Hello, welcome to the video lecture series on digital image processing. So, we have another operation, uh, another kind of filtering operation which is called constant least square filtering. So, now we will consider a filtering operation which is called constrained least square filter. Now, unlike in case of Wiener filtering, where the performance of the Wiener filtering depends upon the correct estimation of the value of k, that is the performance of Wiener filtering depends upon how correctly you can estimate what is the power spectrum of the original undegraded image. In case of this constant least square filter, it does not make any assumption about the original undegraded image. It makes use of only the noise probability distribution function, probability density function noise PDF, and mainly it uses the mean of the noise, which we will write as say m eta, and the variance of the noise, which we will write as sigma eta square. So, we will see that how the reconstruction using this constant least square filter approach makes use of these noise parameters like mean of the noise and the variance of the noise. In case of this constant least square filter, to obtain this constant least square filter, we will start with the expression that we got in our first class, that is G equal to H f plus n. So, you remember that this is an expression which we had derived in the first class, which tells us that what is the degradation model for degrading the image, where H is the matrix which is derived from the impulse response H x and n is the noise vector. Now, here you will notice that the value of H is very sensitive to noise. So, to take care of that, what we do is we define an optimality criteria, and using that optimality criteria, the reconstruction has to be done. And because this degradation function H or the degradation matrix H is noise dependent, it is very sensitive to noise. So, for reconstruction, the optimality criteria that we will use is the image smoothness. So, we know from our earlier discussion that the second derivative operation or the Laplacian operator, it tries to enhance the irregularities or discontinuities in the image. So, if we can minimize the Laplacian of the reconstructed image, that will ensure that the reconstructed image will be smooth. So, our optimality criteria in this particular case is given by C is equal to double summation del square f x y square, where y varies from 0 to capital N minus 1 and x varies from 0 to capital M minus 1. So, our assumption is the image that we are trying to reconstruct, or the blurred image that we have obtained, that image is of size capital M by capital N. So, our optimality criteria is given by this, where del square f x y is nothing but the Laplacian operation. So, this optimality criteria is Laplacian operator based. And our approach will be that we will try to minimize this criteria subject to the constraint that G minus H f hat square should be equal to n square, where this f hat, this is the reconstructed image. So, we will try to minimize this optimality criteria subject to the constraint that g minus h f hat square is equal to n square, and that is why it is called constraint least square filtering. Again, without going into the details of mathematical derivation, we will simply give the frequency domain solution of this particular constraint least square estimation, where the frequency domain solution now is given by f hat u v is equal to h star u v upon h u v square plus a constant gamma times p u v square, this times g u v. Again, as before, this h star indicates that it is the complex conjugate of h. Here again we have a constant term given as gamma, where the gamma is to be adjusted so that the specified constant, that is g minus h f hat square is equal to n square, this constant is met. So, here this gamma is a scalar quantity, scalar constant, whose value is to be adjusted to for so that this particular constant is maintained. And this quantity p u v, the term p u v, it is the Fourier spectrum or the Fourier transform of the mask given by 1 0 minus 1 0, the minus 1 4 minus 1 0 minus 1 0. So, this is my p x y, and this p u v is nothing but the Fourier spectrum of or the Fourier transformation of this p x y. And you can easily identify that this is nothing but the Laplacian operator mask or the Laplacian mask that we have already discussed in our earlier discussion. Now, here for implementation of this, for computation of this, you have to keep in mind that our image is of size capital M by capital N. So, before we compute the Fourier transformation of p x y, which is given in the form of a 3 by 3 mask, we have to pad appropriate number of zeros, so that this p x y also becomes a function of dimension capital M by capital N, or an array of dimension capital M by capital N, and after only converting this to an array of dimension capital M by capital N, we can compute p u v, and that p u v has to be used in this particular expression. So, as we said that this gamma has to be adjusted manually for obtaining the optimum result, and the purpose is that this adjusted value of gamma, the gamma is adjusted so that the specified constant is maintained. However, it is also possible to automatically estimate the value of gamma by an iterative approach. So, for that iterative approach, what we do is we use define a residual vector, say r, where this residual vector is nothing but r equal to g minus h f hat. So, remember that this g is obtained from the degraded image, the matrix degradation matrix H is obtained from the degradation function H x, and f hat is actually the estimated restored image. Now, here since f hat, we have seen earlier that f hat we have seen earlier that f hat u v, and so this f hat in the spatial domain, they are functions of gamma. So, obviously, r which is a function of f hat. So, this r will also be a function of gamma. Now, if I define a function say phi of gamma, which is nothing but r transpose r, or which is nothing but the Euclidean norm of r, it can be shown that this function is a monotonically increasing function of gamma. That means, whenever gamma increases, this Euclidean norm of r also increases. If gamma decreases, the Euclidean norm of r also decreases. And by making use of this property, it is possible to find out what is the optimum value of gamma within some specified accuracy. So, our approach in this case, our aim is that we want to estimate the value of gamma such that the Euclidean norm of r, that is r square, will be equal to n square plus minus some constant a, where this a is nothing but what is the specified accuracy factor, or this gives you the tolerance of reconstruction. Now, obviously, here you find that if r square is equal to n square, then the specified constant is exactly met. However, it is very difficult. So, you specify some tolerance by giving the accuracy factor a, and we want that the value of gamma should be such that r will be, the Euclidean norm of r will be within this range. Now, given this background, an iterative approach, iterative algorithm for estimation of the value of gamma can be put like this. So, you select an initial value of gamma, then compute phi gamma, which is nothing but Euclidean norm of r. Then you terminate the algorithm if r square is equal to n square, here it has been written as eta square plus minus a. If this is not the case, then you proceed to step number 4, where you increase the value of gamma, and if r square is less than eta, increase the value of gamma if r square is less than eta square minus a, or you decrease the value of gamma if r square is greater than eta square plus a. Now, using whatever new value of gamma that you get, you recompute the image, and for that the image reconstruction function, as we have said in frequency domain, is given by this particular expression. And with this reconstructed value of f, you go back to step number 2 and you do this iteration until and unless this termination condition, that is r square is equal to n square plus minus a, this condition is met. Now, using this kind of approach, what we have obtained is, we have got some reconstructed image. So, here you find that it is the same original image, this is the degraded version of that image. On the bottom row, the left hand side gives you the reconstructed image using the Wiener filtering, and again on the bottom row on the right hand side, this gives you the reconstructed image which is obtained using the constant least square filter. The same for the motion degraded image. Here we have also considered some additive noise. So, again on the top row on the left, this is the image which is obtained by direct inverse filtering, and you find the prominence of noise in this particular case. The right one is the one which has been obtained by Wiener filtering. Here also you find that the amount of noise has been reduced, but still the image is noisy, and the bottom one is the one that has been obtained by using the constant least square filtering. Now, if you look at these three images, you find that the amount of noise is greatly reduced in the bottom one, that is this particular image which has been obtained by this restored image, which has been obtained by constant least square filtering approach. And as we said that the constant least square filtering approach makes use of the estimation of mean of the noise and the standard deviation of the noise. So, it is quite expected that the noise performance of the least square constant least square error filter will be quite satisfactory. And that is what is observed here, that this image which is obtained using this constant least square filter, the image has been the noise has been removed to a great extent, whereas the other reconstructed image cannot remove the noise component to that extent. However, if you look at these reconstructed images, the reconstruction quality of this image is not that good. So, that clearly says that using the optimality criteria, that reconstructed image that you get, the optimum reconstructed image may not always be visually the best. So, to obtain a visually best image, the best approach is you manually adjust that particular constant gamma. Now, as I said that this constant least square filtering approach makes use of the noise parameters, that is mean of the noise and the variance of the noise. Now, how can we estimate the mean and variance of the noise from the degraded image itself? It is possible that if you look at a more or less uniform intensity region in the image, if you take a sub image of the degraded image where the intensity is more or less uniform, and if you take the histogram of that, the nature of the histogram is same as the probability density function PDF of the noise which is contaminated with that image. So, we can obtain the noise estimate, or we can compute the noise term, that is eta square, in our expression which is used for this constant least square filtering. In this way, we have the noise variance which is given by say sigma n square, sigma eta square, which is nothing but 1 upon capital M into capital N into double summation eta x y minus m eta, which is the mean of the noise square, where y varies from 0 to capital N minus 1 and x varies from 0 to capital M minus 1. And the noise mean, that is m eta, is given by the expression 1 upon capital M into capital N, then double summation eta x y, where again y varies from 0 to capital N minus 1 and x varies from 0 to capital M minus 1. Now, from this you find that this particular term, this is nothing but what is our eta square. So, by making use of this and making use of the mean of the noise, we get that eta square, this noise term, is nothing but capital M into N, where M into N is M and N the dimension of the image, into sigma n square, sigma eta square minus m eta. And as in our constant that we have specified, it is the eta square which is used in the constant term and which is only dependent upon sigma eta and m eta. So, this clearly says that this optimum reconstruction is possible if I have the information of the noise standard deviation or the noise variance and the noise mean. Now, the estimation of noise variance and noise mean is very important. If I have only the degraded image, what I will do is I will look at some uniform gray level region within the degraded image, find out the histogram of that particular region, and the nature of the histogram is same as the probability density function of the noise. So, as has been shown here in this particular diagram, here you find that this bar that has been shown, this is taken from one such noisy image and this is the histogram of this particular region. And this histogram tells you that what is the PDF of the noise which is contaminated with this image. So, once I have this probability density function, from this I can compute what is the standard or the variance sigma eta square, and I can also compute what is the mean, that is m eta. And in most of the cases for the noise term, the noise is assumed to be 0 mean. So, this m eta is equal to 0. So, what is important for us is only this sigma eta square, and using this sigma eta square we can go for optimum reconstruction of the degraded image. Now, in some situations, in many cases, it is also possible that the image is contaminated with periodic noise. So, how do we remove the periodic noise present in the image? You will find that if you take the Fourier transformation of the periodic noise and display that Fourier transformation, in that case, because the noise is periodic, the corresponding dots, at the corresponding UV location in the Fourier transformation plane, you will get very bright dots, and that dot indicates that what is the frequency of the periodic noise present in the image. Then we can go for a very simple approach, that once I know the frequency components, I can go for band pass filtering just to remove that part of the coefficients from the Fourier transform, and whatever is the remainder Fourier coefficients we have, if we go for the inverse Fourier transformation of that, we will get the reconstructed image. So, as has been shown here. So, here you find that we are taking the same image which we have taken a number of times earlier, and if you look at the rightmost image and if you look closely to this rightmost image, you find that this is contaminated with periodic noise. And if I take the Fourier transform of this, here you find that in the Fourier transform there are few bright dots, one bright dot here, 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 one is at this location and one is at this location. So, all these bright dots tell us that what is the frequency of the periodic noise which contaminates the image. So, once I have this information, I can go for an appropriate band pass filtering to filter out that region from the Fourier transform or that part of the Fourier coefficients. So, that is what has been shown next. So, this is what is a band reject filter. So, this is the perspective plot of an ideal band reject filter, and here the band reject filters are shown superimposed on the frequency plane. So, on the left what I have is an ideal band reject filter, and on the right what I have is the corresponding Butterworth band reject filter. So, by using this band reject filter, we are removing a band of frequencies from the Fourier coefficients corresponding to the frequency of the noise. So, after removal of this these frequency components, if I go for inverse Fourier transform, then I am going to get back my reconstructed image, and that is what we get in this particular case. So, here you find that on the left top, this is again the original image. On the right top, it is the noisy image contaminated with periodic noise. If I go for ideal band reject filter and then reconstruct, then this is the image I get, which is on the bottom left. And if I go for the Butterworth band reject filter, then the image, reconstructed image that I get is in the bottom right. So, we have talked about the reconstruction or the restoration of images using various operations, and the last one that we have discussed is if we have an image contaminated with periodic noise, then we can make use of band reject filter, do frequency domain operation, employ a band reject filter to remove those frequency components, and then go for inverse filtering to reconstruct the image. And here you find that the quality of the reconstructed images are quite good where we have used this band reject filter in the frequency domain. So, with this we complete our discussion on image restoration. Now, let us have some questions on today's lecture. So, the first question is, what is the advantage of Wiener filter over inverse filter? The second question, what is the drawback of Wiener filter? Third one, under what condition Wiener filter and inverse filters become identical? Fourth one, what is the difference between Wiener filter and constraint least square error filter? And the last question, how you can estimate the noise parameters from a given noisy image or from a given blurred image. Thank you.